What if the universe has already shown us something impossible, and we've been staring right at it all along? Tonight, we journey to the edge of what science can explain, where the laws of physics begin to blur. Welcome to Cosmic Drift. Voyager 1 entered interstellar space in 2012. It has never left the solar system. On 18 November 2026, it will become the first human-made object one light day from Earth. Those three statements sound as if they cannot all be true. They can, because they describe three different boundaries. One is made by the sun's plasma. One is made by the sun's gravity. The newest is made by the travel time of light. Voyager crossed the plasma boundary when its instruments found interstellar particles and a much denser plasma beyond the heliopause. It has not crossed the distant region of comets still held by the sun, a journey NASA estimates could take about 30,000 more years. And one light day is not a wall at all. It is the moment a command needs 24 hours to arrive, and a prompt reply needs another 24 hours to return. That is the first useful map of Voyager's position. Not one edge, but three. Picture the smallest of them first. The sun constantly throws out a thin stream of charged particles, called the solar wind. Those particles carry part of the sun's magnetic influence with them. Together they inflate a vast, shifting bubble in the material between stars. That bubble is the heliosphere. Its outer surface is the heliopause. Voyager 1 passed through that surface on 25 August 2012. Outside, it lies interstellar space, because the plasma around the spacecraft is no longer dominated by the outward solar wind. Yet the sun's gravity reaches much farther. It holds planets, dwarf planets, asteroids, and distant comets. Some of those comets occupy an inferred reservoir called the Oort Cloud. Voyager has not reached its inner part. The third boundary has no particles, comets, or magnetic fields to announce it. On 18 November 2026, at 2 hours, 16 minutes, and 7 seconds after midnight in Pacific Standard Time, NASA projects that Voyager 1 will be 16,094,799,096 miles from Earth. That is 25,902,068,356 kilometers, the distance light travels in 24 hours. If a deep space network antenna sends a command at that moment, the radio wave will race outward at the fastest speed information can travel. It will still need a full day to reach the spacecraft. Even if Voyager could execute the command and answer immediately, the reply would need a second day to return. The shortest possible conversation would therefore take about 48 hours, before adding the time needed to run the command, package the result, and schedule the antennas on Earth. Nothing changes in the space around Voyager at that instant. No alarm sounds on board. No sensor jumps. No invisible gate opens. What changes is the relationship between the spacecraft and the people operating it. Distance has turned into delay. This is why the approaching milestone matters. It does not reveal that Voyager has found something new. It reveals what every fact from Voyager now costs in time. It also forces a more careful question than whether the spacecraft is simply inside or outside the solar system. What has Voyager truly left? What has it not left? And what happens to science when every question asked from Earth takes nearly 2 days to answer? If this sharper map of our place in space is worth keeping, you can subscribe and continue the journey with me. The map begins with a radio signal already on its way. At this distance, the signal is not a live picture of Voyager. The spacecraft's cameras were switched off in 1990. Its current science arrives as measurements made by 2 surviving instruments. One measures magnetic fields. The other detects electrical oscillations in plasma. Engineering channels report temperatures, voltages, computer states, and other signs that the machine is still functioning. When those numbers reach Earth, they describe a spacecraft as it was almost a day earlier. Controllers can inspect the report, design a response, test the command sequence, and transmit it. But the spacecraft they are trying to help has continued operating during the whole delay. By the time the command arrives, the condition that inspired it is almost 2 days old from Earth's point of view. By the time a confirming reply returns, roughly another day has passed. That does not mean Voyager is helpless between messages. It was designed to act on its own when basic faults occur. Its command computers contain routines that detect problems and take protective action. Its attitude system keeps the large radio dish pointed toward Earth. Its thrusters make tiny corrections. Its power system distributes a diminishing supply of electricity among the loads that still matter. Autonomy does not make the delay disappear. It changes the kind of conversation that is possible. A terrestrial engineer can watch a machine respond in real time, stop a test when something goes wrong, and try another setting. Voyager offers no such loop. Every command is closer to a carefully prepared letter. It must make sense when it arrives, even though the sender cannot see the spacecraft's current condition. The 3.7 meters high gain antenna is central to this relationship. It is the broad white dish visible in almost every illustration of Voyager. The dish does not search the sky like a telescope. It concentrates radio energy along a narrow direction. To send useful data across billions of miles, Voyager must keep that direction aimed toward Earth with extraordinary consistency. The task is stranger than it first appears. Earth is not fixed. It circles the sun. The ground antenna receiving Voyager's signal rides a rotating planet. The spacecraft follows its own escape trajectory above the plane where most planets orbit. Navigation teams predict these motions, and the spacecraft's attitude system maintains the pointing that makes the link possible. The radio wave spreads as it travels. Its energy is diluted across an expanding area. By the time a Voyager signal reaches Earth, it is fantastically weak. The Deep Space Network uses 34 meters and 70 meters antennas, sensitive receivers, precise timing, and error-correcting methods to recover meaning from that faint arrival. The result can be a stream of data at only a small fraction of the rate used by ordinary digital devices. Voyager's normal interstellar telemetry rate is often given as 160 bits per second. A modern phone moves more information in a blink than Voyager can return in many minutes. Yet rate alone misses the achievement. The spacecraft is not sending entertainment or a dense image. It is sending selected measurements from a location no other working mission occupies. Every bit has crossed the full distance without a relay station, cable, or closer spacecraft to help it home. The Deep Space Network is spread across 3 widely separated regions of Earth. As the planet rotates, one site can lose sight of a distant mission, while another gains it. That arrangement gives deep space missions long viewing opportunities. But Voyager does not own the network. Mars missions, planetary probes, and space observatories also need antenna time. A Voyager command and return must fit within an operational schedule, as well as the laws of light. So the 48-hour round trip is a clean physical minimum, not a promise that every exchange completes in exactly 2 days. A command must be built. A suitable antenna must be available. The spacecraft must receive and execute it. The answer must be transmitted at the right time and captured on Earth. Then people must interpret what came back. This is the first consequence of the 1 light day milestone. The greater the delay, the more knowledge and control separate. The flight team knows a great deal about Voyager's design, history, and expected state. What it cannot know is the spacecraft's present condition. Present is the one thing the radio link can never deliver. The distinction matters whenever the spacecraft shows a fault. Suppose a voltage falls below a safe limit. Voyager's onboard protection may switch off equipment before Earth sees the first warning. Nearly a day later, the warning arrives. Engineers reconstruct what probably happened, but the spacecraft is already living in the consequence. A response sent that day reaches it the next day. The result comes home the day after that. This is not a flaw in Voyager. It is the geometry of causation. Information cannot outrun light. No larger antenna, stronger transmitter, or cleverer code can erase the travel time. Better hardware can make a weak signal readable. It cannot make an event arrive before the wave carrying news of it. That simple rule links the approaching milestone to the entire mission. Voyager became an interstellar probe because it was given an extraordinary trajectory. It remained a scientific probe because its instruments could recognize a boundary no camera could photograph. It remains a working probe because engineers learned to make decisions across a delay that has grown from minutes to almost a day. To understand how a machine built in the 1970s reached such a position, begin with a coincidence of moving worlds. Jupiter, Saturn, Uranus, and Neptune do not hold fixed places in the sky. Each follows the Sun at a different speed. Once in roughly 175 years, their changing positions allow a spacecraft to move from one giant planet toward the next with unusual efficiency. The planets do not form a neat line. The useful geometry is a sequence of encounters, each reached at the right time and angle. Mission designers can use a close planetary flyby to change a spacecraft's path and speed relative to the Sun. This is called a gravity assist. It is sometimes described as stealing energy from a planet, which is vivid but incomplete. The spacecraft falls into the planet's moving gravitational field, curves around it, and leaves in a different direction. Because the planet itself is moving around the Sun, the spacecraft can gain heliocentric speed, while the planet loses an immeasurably small share of its orbital energy. The encounter is not free propulsion in the spacecraft's own frame. Gravity accelerates the craft while it approaches, and slows it while it departs. Relative to the planet, those changes balance apart from small-powered corrections. Relative to the Sun, however, the moving planet has redirected the velocity vector. The new direction and timing can send the spacecraft toward another world. For the outer planets, that geometry was precious. A direct journey to Neptune using the technology and launch vehicles of the era could take roughly 30 years. The sequence of gravity assists could reduce the trip to about 12. The alignment offered access to worlds that had never been seen close up, within the working lifetime of a mission team and its hardware. The original grand vision considered 4 spacecraft visiting the outer planets and Pluto. Cost and risk reduced that ambition. Voyager 1 and Voyager 2 were officially built for close studies of Jupiter and Saturn. Their prime mission was expected to last about 5 years. The machines carried enough flexibility, redundancy, and reprogrammable capability to do more if the encounters succeeded. More than 10,000 possible trajectories were studied. The chosen routes had to satisfy scientific desires and unforgiving geometry. They needed close looks at Jupiter, its moons, Saturn, its rings, and Titan. Voyager 2's path also preserved a chance to continue toward Uranus and Neptune. Voyager 1's path pursued a different prize. Voyager 2 launched first, on 20 August 1, 1977. Voyager 1 followed on 5 September, but its shorter and faster route allowed it to overtake its twin before the year ended. The names reflect the order in which the spacecraft would reach the first target, not the order in which they left Earth. The spacecraft rode a Titan 1 Li Centaur rocket away from Cape Canaveral. Voyager 1 left Earth with a large dish, long booms, 3 radioisotope thermoelectric generators, computers, thrusters, and instruments arranged around a compact central body. It was not built like a sleek vessel from fiction. It was a careful distribution of fields of view, radiogeometry, balance, heat, and electromagnetic interference. The 3 generators carried plutonium fuel whose decay produced heat. Thermocouples converted part of that heat into electricity. There were no solar panels because sunlight becomes too weak for a practical 1970s spacecraft power system at the giant planets. The generators could provide power far from the sun, but not forever. Their output would slowly decline as the fuel aged and the thermocouples degraded. The computers were modest even by later standards. Voyager carries paired systems for command, attitude control, and flight data. Their memories are measured in thousands of words, not gigabytes. That limitation can sound like a comparison trick until its consequence becomes clear. The spacecraft cannot receive a modern software stack. Every change has to fit within a tiny, already occupied machine whose original designers worked before the personal computer era. Redundancy gave the mission alternatives. Duplicate computers, multiple thruster branches, separate transmitters, and protective routines allowed the team to route around some failures. Reprogrammability gave those alternatives new uses. Hardware intended for one part of the planetary mission could later solve a problem its designers had not expected to face half a century away. Voyager 1 reached Jupiter in early 1979. Its closest approach came on 5 March. The cameras began returning images that surpassed Earth-based views, while the spacecraft was still approaching. By the end of the encounter, Voyager 1 had taken nearly 19,000 pictures, and its instruments had measured magnetic fields, particles, radio emissions, atmospheres, rings, and moons. Jupiter was not a quiet sphere with a few fixed markings. The images showed bands and storms changing through time. The magnetic environment was immense and violent. A thin ring appeared around the planet. The mission found two small moons, Thebe and Metis. The greatest surprise came from Io. A plume rising above the moon's edge revealed active volcanism, the first observed on another world. Io's interior is continually flexed by the competing gravity of Jupiter and neighboring moons. Friction from that tidal deformation produces heat. Material from Io feeds Jupiter's magnetic environment, linking the geology of a moon to a planetary system far larger than the moon itself. That discovery changed the mental model of the outer solar system. A small, cold-looking world could be more volcanically active than Earth, not because sunlight warmed it, but because gravity repeatedly distorted it. Voyager did not merely add a moon to a catalog, it revealed a mechanism that made apparently frozen distance dynamic. Jupiter's gravity also changed Voyager. The encounter bent its path toward Saturn and altered its speed around the Sun. The scientific target and the engine were the same planet. Voyager 1 reached Saturn on 12 November 1, 1980. The rings resolved into an intricate system of narrow features, gaps, waves, and interacting material. New moons and a new ring joined the known system. But the encounter that determined Voyager 1's future was with Titan. Titan was already known to possess a substantial atmosphere. A close pass promised measurements that could not be made from a safer distance. The chosen trajectory sent Voyager 1 near the moon and then carried it behind Saturn's rings. Titan's gravity and the Saturn encounter together bent the spacecraft northward, out of the ecliptic plane where the major planets travel. The decision had a permanent cost. A different aim point might have preserved another planetary destination, including a theoretical route toward Pluto. The Titan route ended that possibility for Voyager 1. After Saturn, no planet waited ahead. This was not a navigation mistake. Titan was a primary objective. The flyby strengthened evidence for a dense, nitrogen-rich atmosphere and an opaque organic haze. The spacecraft gave up future planets in exchange for the best encounter the science team had chosen. That exchange is the hidden origin of Voyager 1's interstellar trajectory. It was not launched from Earth toward a marked doorway in the heliosphere. It was launched toward Jupiter and Saturn. The gravity assists and the Titan choice created the outward path. Interstellar space became a possible destination because the planetary mission succeeded. After the last encounter, the spacecraft was still healthy, powered, and moving faster than the Sun could call it back. Its path was hyperbolic relative to the Sun. In ordinary language, that means it had enough speed to escape, rather than settle into a long, closed orbit. Yet escape has several meanings, just as leaving has several boundaries. Voyager was gravitationally unbound from the Sun, in the sense that its trajectory would not loop back. It was still physically located among objects and plasma influenced by the sun. A ticket out is not the same as already being outside. The distinction will return at the Oort Cloud. First, the mission had to learn what a spacecraft does when its last planet falls behind it. For Voyager 1, the answer began with subtraction. Planetary encounters had demanded cameras, scan platform movements, high data rates, and rapid changes in the observation plan. The Interstellar mission would demand endurance. Systems built for close views of bright worlds became unnecessary. Heaters and instruments that no longer served the new purpose could be turned off. The spacecraft would spend most of its time keeping its antenna aimed at Earth and measuring the particles, fields, and waves along a single outward line. The transition was not immediate. After Saturn, Voyager continued returning data about the distant solar system. Its ultraviolet instrument observed stars and the distribution of hydrogen. Particle instruments watched the solar wind change with distance. The magnetometer followed the sun's field outward. Engineers kept learning how the spacecraft aged. In 1990, Voyager 1 received a final photographic assignment. It turned its cameras back toward the planets it had left. From roughly 3.8 billion miles, or 6.4 billion kilometers, it assembled a family portrait of the solar system. Earth occupied less than a pixel in one frame, caught within scattered sunlight. The image later became known as the pale blue dot. Its power did not come from new detail. It came from the absence of detail. Oceans, continents, weather, cities, and every living person were compressed below the camera's ability to resolve them. The image converted distance into a loss of visible distinction. After that portrait, the cameras were switched off on 14 February 1990 to conserve power and memory for the continuing mission. They have not photographed interstellar space. Any current image that shows Voyager among stars is an artist's concept, a reconstruction of the spacecraft against a background it cannot record with its own cameras. That matters because current Voyager stories are often illustrated as if the probe were still an eye. It is not. The surviving mission is closer to touch and hearing, though even those words need care. The magnetometer samples the magnetic field at the spacecraft. The plasma wave instrument measures changing electric fields. Scientists can translate some of those oscillations into audible frequencies for analysis or public demonstration, but there is no microphone recording sound traveling through a vacuum. The loss of the camera did not make Voyager blind in a scientific sense. It changed what counted as evidence. A photograph locates visible light by direction and intensity. A particle counter records arrivals. A magnetometer measures a local field. A plasma wave receiver detects oscillations. Each instrument answers a different physical question, and none can be replaced simply by making a picture. Voyager's official interstellar mission began in 1990. Its first major distance record came later. On 17 February 1998, Voyager 1 passed Pioneer 10 in distance from the Sun and became the most distant human-made object. The two spacecraft did not pass each other in space. They traveled in different directions. Voyager merely crossed the invisible radius that placed it farther from the Sun. Again, the record was not a physical boundary. No instrument could detect the moment. It was a comparison calculated from trajectories. Yet such records help translate a path that has no nearby landmarks. Voyager crossed 100 astronomical units in 2006. 1 astronomical unit is approximately the mean distance between Earth and the Sun. At 100 of them, the entire planetary system lay far behind, but the Sun's moving plasma still surrounded the spacecraft. Voyager also carries an object meant for a future without radio contact. Bolted to the spacecraft is a 30 centimeters gold-plated copper disc known as the Golden Record. Its 115 images are encoded in analog form. Its audio includes natural sounds, greetings in 55 languages, and about 90 minutes of music chosen from different cultures and periods. A protective cover carries symbolic instructions for playback and information intended to locate the record's origin. The record is not a serious attempt to arrange a meeting. Space is too large, the spacecraft is too small, and no known recipient waits along its path. NASA's own description makes the condition explicit. It would be encountered and played only if an advanced spacefaring civilization happened to find it. That possibility belongs to speculation. The artifact does not provide evidence of extraterrestrial life, and it has not received a reply. Its factual importance lies elsewhere. The Golden Record was built for a timescale longer than the working electronics. It separates Voyager as a mission from Voyager as an object. While the mission lives, the spacecraft is part of a chain of measurement and response. A sensor changes. A computer formats the result. A transmitter turns electrical patterns into radio waves. The Deep Space Network receives them. Scientists interpret the data, and engineers may send new instructions. When that chain ends, the object continues on the same trajectory, but the scientific relationship is broken. This difference between mission and object will become the final boundary in Voyager's story. It is not a boundary in space. It is the last successful exchange of information. No one knows its date. Long before that unknown ending, Voyager encountered a boundary that its creators hoped it might reach, but could not place precisely. The Sun does not end at its visible surface. The hot outer atmosphere releases a continual flow of electrons, protons, and heavier ions. Close to the Sun, magnetic fields and extreme heat help accelerate this solar wind. By the time it passes Earth, the flow often moves at hundreds of kilometers per second. It continues past every planet. The material between stars is also not empty. The local interstellar medium contains thin plasma, neutral atoms, dust, magnetic fields, and energetic particles. The Sun moves through this environment. The solar wind pushes outward while interstellar material and pressure resist it. Their interaction creates the heliosphere. Bubble is a useful first picture, but a bubble suggests a fixed, smooth sphere. The heliosphere is neither fixed nor exactly spherical. Solar activity changes the wind. The Sun moves through its local galactic environment. Magnetic fields and charged particles alter the flow. Global models produce different shapes depending on which physics and observations they emphasize. At Voyager 1's path, the first major transition arrived before the heliopause. The outward solar wind was moving faster than the speed at which pressure disturbances could travel through that plasma. In 2004, the flow slowed abruptly at the termination shock. The word shock does not mean that Voyager struck matter like a vehicle hitting a barrier. A collisionless shock can form in a plasma because particles and electromagnetic fields collectively transfer energy and momentum. Individual particles do not need to collide like air molecules in an ordinary shock wave. The organized field interaction changes the population and slows the bulk flow. Voyager 1 crossed the termination shock on 16 December 2004, near 94 astronomical units from the Sun. Inside that boundary, the solar wind moved outward at supersonic speed relative to the relevant plasma waves. Beyond it, the flow was slower, hotter, and compressed. The spacecraft entered the heliosheath. The heliosheath was a region of changed solar wind, not yet interstellar space. Solar material still dominated important particle populations. The magnetic field still carried the Sun's signature. The flow had slowed and begun turning around the heliosphere rather than continuing straight outward. This gives us a physical map with three related regions. The supersonic solar wind occupies the inner heliosphere. The termination shock slows it. The heliosheath carries the disturbed and redirected flow toward the heliopause. Beyond the heliopause, interstellar plasma dominates. The names are less important than the behavior. Fast outward flow becomes slow diverted flow. Then the source of the surrounding plasma changes. No mission before Voyager had crossed this route. Models could estimate the distances, but the boundaries move as solar and interstellar pressures change. Voyager provided a single track through a vast three-dimensional interaction. It could measure what happened at its location, not photograph the whole heliosphere from outside. This is a crucial limit on the evidence. When an illustration shows the heliosphere as a comet-shaped bubble or a rounded croissant, the image is a model, not a picture returned by Voyager. Other missions observe energetic neutral atoms that help map the interaction from nearer the Sun. Computer simulations connect those observations to plasma physics. Voyager supplies the only kind of evidence a local crossing can provide, a sequence of measurements along its path. During the years after 2004, the particle environment changed. The solar wind's outward speed along Voyager's radial direction approached zero. Energetic particles behaved in unexpected ways. Researchers watched for a combination of signs that would mark the heliopause. One expected sign involved particles born inside the heliosphere. Low-energy ions accelerated within the Sun's domain should decline when the spacecraft left. Another involved galactic cosmic rays. These are highly energetic particles arriving from beyond the heliosphere. The solar wind and its magnetic turbulence impede many of them, so their intensity should rise outside the solar bubble. A third sign involved plasma density. The outer heliosphere contains extremely thin solar plasma. The local interstellar plasma was expected to be denser. A marked increase would be powerful evidence of a new environment. A fourth involved magnetic field direction. Many scientists expected the interstellar magnetic field to point differently from the solar field carried outward by the wind. A large directional rotation seemed like a natural boundary marker. The difficulty was that nature did not change every sign in the simplest expected way. In 2012, Voyager 1 entered a region where the particle counts shifted dramatically. Several times, low-energy particles associated with the heliosphere dropped, while galactic cosmic rays rose. Some changes reversed. Then, around 25 August, the heliospheric particles fell and stayed low, while galactic cosmic rays reached a higher level and remained there. That looked like a crossing. The spacecraft appeared to have moved beyond the population of particles trapped and accelerated within the heliosphere. But the magnetic field direction did not swing as much as many researchers had predicted. The mismatch created a real scientific collision. One set of instruments said the particle environment had changed decisively. The magnetometer said the field maintained a surprisingly familiar direction. Had Voyager crossed the heliopause, or had it entered a final region still inside it, with magnetic pathways allowing particles to escape and enter? Researchers used names such as magnetic highway for the intermediate interpretation. The phrase described field lines that seemed connected in a way that let solar particles stream outward and galactic particles stream inward. It did not prove a literal road or a stable new zone. It recorded an attempt to explain an unexpected combination of measurements. This is how a boundary becomes evidence rather than decoration. A model makes several predictions. Instruments return a mixture of expected and unexpected changes. The team does not choose the most dramatic sign and ignore the rest. It asks which physical interpretation can account for all of them. The decisive clue came from an instrument that did not count plasma particles directly. Voyager 1 was launched with a plasma science instrument designed to measure the speed, density, temperature, and pressure of ionized gas. Its orientation became unfavorable after the Saturn encounter, and its performance degraded. The instrument was switched off in 2007. When Voyager approached the heliopause, it could not provide the direct plasma measurements researchers wanted. The plasma wave subsystem offered another route. Plasma is a gas in which some electrons are no longer bound to individual atoms. If the electrons are displaced from the heavier positive ions, electrical forces pull them back. The electrons can oscillate collectively. The natural frequency of that oscillation depends on the electron density. More electrons per unit volume produce a higher characteristic plasma frequency. The relationship is not an analogy, it is a measured property of plasma. If an instrument detects the relevant oscillation frequency and the physical mode is correctly identified, scientists can infer the local electron density. Voyager's plasma wave instrument uses long antennas to detect changing electric fields. It does not need to collect the electrons in a cup. It senses the electrical signature of their collective motion. For much of the time, the surrounding plasma did not oscillate strongly enough at the needed frequency to produce an obvious event. A disturbance from the sun supplied the excitation. Powerful solar eruptions launched shocks outward. Months later, after crossing the outer heliosphere, one of those disturbances reached the plasma around Voyager and made it ring. The instrument detected oscillations in late 2012 and again in spring 2013. Their frequencies indicated electron densities far above those expected in the outer heliosphere. The values were consistent with the local interstellar medium. Because the stronger 2013 event occurred after the suspected crossing, researchers could use the density pattern and the earlier particle changes to reconstruct where Voyager had entered the interstellar plasma. The mission team identified 25 August 2012 as the heliopause crossing date. The conclusion was a strong inference built from direct measurements. Voyager directly recorded particle counts, magnetic fields, and plasma wave frequencies. The boundary itself was not photographed. Scientists inferred the crossing from the coordinated changes and the physics linking plasma frequency to density. That distinction does not weaken the result. Most of science works by connecting measurements to physical causes. A thermometer does not show heat as an object. It measures a property that changes with temperature. A spectrometer does not catch a label naming an element. It detects wavelengths whose pattern reveals the atom. Voyager's plasma wave system detected an electrical frequency whose value revealed the density around it. The numbers made the transition hard to dismiss. The density expected in the outer heliosphere was around 0.002 electrons per cubic centimeter. The inferred interstellar density was closer to a few hundredths, or roughly 0.1 electron per cubic centimeter, depending on the event and time. Both are near vacuum by everyday standards, but the relative increase was large. Imagine comparing two nearly empty stadiums. One contains a single grain floating through an enormous section of space. The other contains dozens in the same volume. Neither looks crowded. The difference still changes how waves travel and reveals that the material has a different origin. The magnetic direction remained important. The result did not prove that every expectation about the heliopause had been correct. It showed that the field beyond the boundary could remain aligned more closely with the heliospheric field than a simple picture suggested. The interstellar magnetic field may drape around the heliosphere, producing a local direction near Voyager that resembles the field inside. Voyager 2 later crossed the heliopause along a different path in November 2018. Its plasma instrument was still operating then, allowing direct measurements of the plasma flow and density across the boundary. The two crossings occurred at different distances and under different solar conditions. Together, they confirmed that the heliopause is not a single fixed radius. For Voyager 1, the evidence supports a precise statement. It crossed from plasma dominated by the solar wind into the local interstellar medium. It became the first human-made object to operate in interstellar space. The statement it does not support is equally important. The spacecraft did not cross beyond every object, field, or gravitational influence associated with the Sun. The heliopause is an edge of the heliosphere. Whether someone calls that the edge of the solar system depends on which physical definition the question uses. This is not wordplay added after the fact. Different boundaries answer different questions. Where does the solar wind stop dominating the plasma, the heliopause? Where do the known planets orbit? Far inside it. Where might the most distant long-period comets remain bound? Far beyond it. Where does a radio message take 1 day to arrive? At 1 light day from Earth. Voyager's path gives these definitions a common object. The same spacecraft can be outside one region, inside another, and approaching a third threshold that is not a region at all. Once across the heliopause, Voyager did not enter a finished answer. It entered a place where every measurement was new. Interstellar space is often described as the space between stars. That definition is correct, but easy to misread. It can suggest a uniform void that begins once a spacecraft passes the last local obstacle. The region around Voyager is neither uniform nor free from the sun's effects. The local interstellar medium carries structure. Its density and magnetic field vary. Disturbances launched by the sun can continue through the heliopause and travel outward. The heliosphere itself diverts and compresses material. Voyager is sampling what researchers call the very local interstellar medium, the environment close enough to retain the consequences of the sun's passage and activity. This produces another useful distinction. Outside the heliosphere does not mean beyond all solar influence. The outward solar wind has been stopped and turned, but waves, energetic disturbances, light, gravity, and the heliosphere's presence still connect the region to the sun. Soon after the crossing, the strongest plasma wave detections came when solar eruptions drove shocks into the interstellar plasma. These events were scientifically useful, but they left gaps. If density could be measured only when a large disturbance made the plasma oscillate, Voyager would take isolated samples, separated by long, quiet intervals. Years later, researchers found a much weaker signal between the dramatic events. From 2017 onward, plasma wave data showed a persistent, narrow-band emission. Its frequency changed gradually and appeared to follow the local electron density. Instead of waiting only for a shock to strike the plasma like a hammer, scientists could use the weaker signal to trace density along more of the route. Calling it a hum makes the result memorable, but the word can create the wrong picture. Voyager is not hearing a continuous acoustic tone carried through air. Its antennas detect electrical oscillations. Researchers can map their frequencies into audio that human ears recognize, just as radio astronomy can translate electromagnetic data into sound. The audible result is a representation of measured frequency, not a microphone recording from outside the spacecraft. The physical cause of the persistent emission is not fully settled. Thermally excited plasma oscillations and quasi-thermal noise are among the proposed mechanisms. Future observations may distinguish them. That uncertainty belongs beside the mechanism, not beside the existence of the signal. The emission was measured. Its detailed origin remains under study. The difference shows how certainty can be layered within one result. Direct observation gives the instrument's frequency pattern. Strong inference connects the frequency to changing electron density. Competing explanations address what excites and maintains the weak signal. None of those layers needs to be flattened into either total certainty or total mystery. The magnetometer supplies a different local record. It sits at the end of a 13 meters boom, away from electrical currents in the spacecraft that could contaminate the measurement. It samples the strength and direction of the surrounding magnetic field. The instrument does not show the global field around the entire heliosphere. It records what passes one moving point. That single line can still test broad ideas. A model of the interstellar magnetic field and heliosphere predicts how the field should drape, compress, or fluctuate near Voyager's route. The measured sequence can agree with part of the prediction and challenge another. When Voyager 1 and Voyager 2 sample different directions, their records reveal how strongly one local crossing can vary from another. The limitation is also a source of value. Telescopes and energetic neutral atom detectors can offer broad, indirect views of the heliosphere. Voyager supplies direct local measurements. A global map without a local sample may hide small-scale behavior. A local sample without a global map cannot reveal the entire shape. The methods answer each other's weaknesses. For years after 2012, Voyager 1 also returned particle measurements. The cosmic ray subsystem followed energetic particles arriving from the galaxy. The low-energy charged particle instrument measured ions and electrons and had scanned directions using a small motor that turned its sensor. Those records documented the boundary and interstellar environment. By 2026, both instruments had been switched off to save power. The cosmic ray subsystem went off on 25 February 2025. The low-energy charged particle instrument followed on 17 April 2026. The shutdowns did not mean the instruments had ceased to matter. Their accumulated data remained part of the evidence. It meant the live mission could no longer afford their electrical load. As of 18 August 2026, Voyager 1 has 2 operating science instruments. The magnetometer measures magnetic fields. The plasma wave subsystem detects plasma oscillations. That current count must be attached to a date because the mission is changing. An article from 2024 may correctly describe 4 operating instruments. A current account that repeats the old number would be wrong. The 2 remaining instruments form a narrow but coherent observatory. Plasma density and magnetic field are central properties of the medium. Their relationship shapes waves, pressure, and the motion of charged particles. Voyager no longer measures every part of that system directly, but it still records 2 load-bearing quantities from a place beyond the heliopause. The data are valuable partly because no replacement is nearby. Voyager 2 also operates in interstellar space, but along a different path and at a different distance. A future interstellar probe would require decades of planning and travel. When an instrument on Voyager 1 is switched off, its location cannot be recreated by sending a technician or launching an identical unit next month. This makes each power decision scientific as well as technical. Keeping one instrument alive may require shutting down another. Warming one component may force a different load off. Preserving the radio link can outweigh an observation that would consume the remaining margin. The spacecraft has become an experiment in choosing which senses to retain. The measurements also carry the history of the medium. A plasma disturbance seen far from the Sun may have begun with an eruption many months earlier. By connecting solar observations, heliospheric models, and Voyager's later detection, researchers can follow energy across a distance larger than the heliosphere itself. The Sun is therefore present in Voyager's interstellar science, without dominating the local plasma. It sends disturbances into the medium. Its moving heliosphere shapes the boundary. Its light still reaches the spacecraft. Its gravity still influences Voyager's trajectory, though Voyager has enough speed to escape. Outside is not the same as disconnected. That principle also applies to Earth. Voyager is not physically attached to the planet, but the radio link joins events at two distant locations into one experiment. A measurement does not become science merely because a sensor records it. The result has to be transmitted, decoded, calibrated, compared, and interpreted. The one light-day distance stretches this chain without breaking it. The chain came close to breaking in November 2023. On 14 November, Voyager 1 stopped returning readable science and engineering data. The radio carrier still reached Earth. Controllers could tell that the spacecraft was receiving commands and otherwise operating, but the information inside its transmission was unusable. The link had not gone silent. It had lost meaning. That difference narrowed the search. A transmitter failure might remove the carrier. A pointing error might weaken or erase the received signal. Here, a signal arrived in the expected place, but the pattern-carrying telemetry did not decode into valid data. The flight data subsystem became the focus. This onboard computer packages science and engineering measurements before transmission. It organizes the information so ground systems can recognize and reconstruct it. If the subsystem sends a repeated or corrupted pattern, the radio can work perfectly while the message remains unreadable. The investigation itself moved at interstellar speed. Engineers designed diagnostic commands and waited roughly 22.5 hours for them to reach Voyager at the distance of early 2024. A response needed roughly another 22.5 hours to return. Each useful test could consume almost 2 days of light time before analysis and planning began again. The team could not attach a debugger to the computer or inspect the memory directly. It had to ask the spacecraft to reveal selected states through the very system that was failing to package data correctly. Every test had to minimize the risk of making a recoverable problem worse. In March 2024, the evidence pointed to a single failed memory chip within the flight data subsystem. The chip stored part of the computer's software code. Losing that section did not stop Voyager from receiving commands, but it prevented the subsystem from building readable science and engineering packets. No command could repair the physical chip. The team had to route around it. The obvious solution would be to place the lost code in another memory location. Voyager's memory offered no single free region large enough. The engineers therefore divided the affected code into sections and stored those sections in different places. They also changed references elsewhere in the software, so the separated pieces could still work together. This was not a fresh program written for modern hardware. It was surgery on code designed in another era, inside a computer more than 15 billion miles away, with limited memory and almost a 2-day minimum feedback loop. The repair had to preserve the timing and interactions of routines already running the spacecraft. The team began with the portion responsible for packaging engineering data. A command carrying the change left Earth on 18 April 2024. When the response arrived on 20 April, usable engineering telemetry appeared for the first time in about 5 months. That return was a completed test, not the end of the recovery. Engineering data allowed the team to assess the spacecraft's health. Other code sections still had to be moved and adjusted. Science packaging then had to be restored. On 19 May, controllers sent the next major command to restart science return. 2 instruments resumed normal operation promptly. 2 required further work. By 13 June 2024, all 4 instruments that were active at the time were returning usable science data. The recovery demonstrates why 1 light day distance is more than a large number. A failed chip created a software problem. The software problem was diagnosed through corrupted communication. The workaround had to be designed under tight memory limits. Every step required a command and a delayed answer. The same geometry that makes Voyager scientifically unique also slows every attempt to preserve it. The spacecraft cannot be treated as a frozen museum piece. Its state keeps changing during the diagnosis. Temperatures drift. Power declines. Ground antennas move through scheduled work. Other spacecraft compete for network time. A safe command today may need new assumptions by the time the next test is ready. The repair also reveals the value of design knowledge. Engineers working in 2024 did not have every original builder beside them. Documentation, archived code, hardware models, test facilities, and experience accumulated by the mission allowed a new team to reason about an old machine. Continuity existed in records and practice, rather than in one unbroken group of people. Voyager's computers do not understand the scientific meaning of the data. They execute routines. Human teams decide which measurements matter, which memory can be moved, and which risk is acceptable. The mission is therefore a partnership across time as well as space. Engineers inherit decisions made before many of them began their careers, then add changes that a future team may have to understand. The failed chip was not Voyager's only aging problem. To communicate, the spacecraft must keep the high-gain antenna aimed at Earth. Small hydrazine thrusters control its attitude. The thrusters fire in brief pulses to correct drift and perform rolls. Over decades, residue has accumulated inside some narrow fuel tubes. The openings that deliver propellant have become more restricted. Engineers have switched among different thruster branches to reduce use and preserve alternatives. Voyager carries 2 sets of attitude control thrusters, and another set originally used for trajectory correction during the planetary encounters. The functions overlap but are not identical. Some can control pitch and yaw. Roll control requires suitable thrusters and a working orientation reference. In 2017, the team tested trajectory correction thrusters on Voyager 1 that had not been used for 37 years. They worked and provided another way to point the spacecraft. Later, clogging affected the branch in use, leading to further swaps and careful management. The 2024 thruster work carried a thermal complication. Thruster tubes needed to be warmed before a switch, but the spacecraft's power margin was so small that turning on a heater risked triggering protective shutdown. The team turned off another load, allowed the heater to operate, made the change and restored the configuration. A maneuver that once would have been routine had become a balance among temperature, electricity, and fault protection. In 2025, another problem became urgent. Voyager 1's primary roll thrusters had been considered unusable since 2004, after power was lost in two small internal heaters. The spacecraft relied on backup roll thrusters, but their fuel tubes were clogging. If they failed, keeping the antenna aligned could become much harder. A major deep space network antenna, used to send commands to Voyager, was also approaching a period of maintenance. The team wanted another roll control option before that ground asset became unavailable for months. Engineers revisited the old failure and found a path that earlier analysis had not used. They commanded the heaters back into operation under tightly controlled conditions and tested the thrusters. The set that had been dormant for 21 years responded. The result is sometimes described as reviving dead thrusters. That phrase captures the time span, but can hide the mechanism. The thrusters did not heal themselves. Engineers re-examined the power configuration, accepted a controlled risk, restored heat, and verified the response through delayed telemetry. The event also illustrates why backup hardware is not simply spare hardware. A redundant branch ages in the same environment. Its seals, heaters, valves, and lines may develop different problems while unused. A backup becomes valuable only if the team still knows how to activate it and can afford the power and risk needed to test it. At almost one light day, pointing is survival. The spacecraft's transmitter can produce a signal, but a large directional antenna aimed away from Earth would place most of that energy elsewhere. Ground stations might detect a weaker mode under some conditions, yet routine science return depends on the dish maintaining its target. The target itself is a moving dot, calculated by navigation. Voyager uses a star reference and thruster pulses to control orientation. Seen along the antenna axis, a roll rotates the spacecraft around the line to Earth. Pitch and yaw move that line. These tiny motions determine whether a 3.7 meters dish can deliver information across more than 25 billion kilometers. The hardware stories are not side adventures, separate from the science. The failed memory chip threatened the meaning of the signal. Thruster clogging threatens its direction. Declining power threatens the instruments that create it. The one light day delay threatens the speed of every intervention. Together, they define what it takes for a measurement to exist on Earth. And every successful repair takes place inside a power budget that cannot be repaired. Voyager 1 carries 3 radioisotope thermoelectric generators. Each contains plutonium-238, an isotope that releases heat as its nuclei decay. Thermocouples convert a portion of the temperature difference between the hot source and colder space-facing parts of the generator into electricity. The system has no turbine and no chain reaction. It is not a small nuclear reactor in the usual sense. Radioactive decay supplies steady heat, and solid-state devices turn some of that heat into electrical power. At launch, each generator produced about 158 watts of electricity. The combined supply had to run computers, communications, heaters, instruments, and support systems. That output has fallen throughout the mission. The plutonium decays, and the thermocouples also become less efficient with age. By 2026, each Voyager was losing about 4 watts of available electrical power per year. 4 watts sounds trivial beside household electricity. Inside a spacecraft already stripped to essential loads, it is a yearly demand to find another system that can be turned off, or another configuration that can run more efficiently. This is not a battery moving toward a known empty mark. The generators continue producing heat and electricity. The problem is margin. The total demand must remain below the available supply, and sensitive components must stay within workable temperatures. A change that saves electrical power can remove heat the spacecraft was quietly relying on. Early in the mission, many instruments and heaters were active. Planetary encounters justified their cost. As Voyager moved outward, the team shut off systems no longer needed and accepted temperatures below original test limits when hardware continued to function. Each successful step expanded practical knowledge of what the spacecraft could survive. That knowledge is empirical. A component tested to one limit on Earth may keep working beyond it in flight, but past survival does not guarantee future survival. Engineers can observe trends, build thermal models, and preserve contingency margins. They cannot prove that an aging part will operate indefinitely. This makes the shutdown order consequential. Years ago, engineers and scientists agreed on a sequence for retiring instruments while preserving a useful scientific combination. The order was not improvised at the instant power ran short. It balanced the uniqueness of each measurement, the electricity saved, instrument health, and the needs of the remaining investigation. The cosmic ray subsystem was turned off first, among Voyager 1's final 4 instruments, in February 2025. It had measured energetic particles through the heliopause crossing and for more than a decade beyond. Its loss narrowed the live view of the interstellar particle population. The low-energy charged particle instrument followed in April 2026. The shutdown sequence itself demonstrates the delay. At more than 15 billion miles, the commands needed around 23 hours to arrive. The planned process aboard the spacecraft took about 3 hours and 15 minutes. Confirmation then had to cross the distance back to Earth. One small part of the instrument remained powered. A motor that rotates the sensor uses about 0.5 watts. Keeping it moving offers a chance, not a promise, that the instrument could be restarted if another power-saving intervention frees enough electricity. Stopping the mechanism for years might make a future revival less likely. This is a striking inversion. Half a watt can decide whether a scientific sense might someday return. The mission is no longer managed in broad categories such as instrument on or instrument off. It is managed motor by motor, heater by heater, and switch by switch. Turning off the low-energy charged particle instrument was expected to provide roughly a year of breathing room under the conditions reported in April 2026. Breathing room is an engineering phrase for restored margin, not an exact extension of the mission to a known date. The rate of power decline is only one threat: a memory fault, thruster problem, thermal excursion, transmitter issue, or unexpected load could change the schedule. The next proposed intervention carries an explosive nickname, but no explosion. The team calls it the Big Bang. The plan is to switch a group of powered devices at nearly the same time and replace their functions with lower power alternatives. Some loads that helped keep the spacecraft warm can be removed if other configurations preserve enough heat for continued operation. The simultaneous change is important because the spacecraft's thermal and electrical systems interact. Turning off one item and waiting too long before activating a substitute could allow a temperature or voltage to move into danger. A coordinated sequence can cross from one stable configuration to another. Voyager 2 served as the first test. By 4 August 2026, NASA reported that engineers had successfully completed the Big Bang power swap on that spacecraft. The savings were expected to keep its 3 instruments operating for at least an additional year before another shutdown would otherwise have been necessary. As of 18 August 2026, NASA had not reported the same operation as complete on Voyager 1. The team planned to perform it in the coming months. That timing matters. A documentary produced now can describe a planned intervention and the successful Voyager 2 precedent. It cannot move the plan into the past or claim the Voyager 1 result before telemetry confirms it. The greater distance makes Voyager 1 the harder case. The command delay is longer. Its power state and active instruments differ from those of its twin. A successful sequence on Voyager 2 reduces uncertainty, but it does not make Voyager 1's result automatic. The name Big Bang also reveals something about mission culture. Teams use compact names to discuss complex operations. Public language can mistake the nickname for the physics. Nothing detonates. The spacecraft does not receive new energy. The operation rearranges a dwindling budget. If the swap succeeds, it may delay another sacrifice. It cannot reverse radioactive decay or restore every retired instrument. Voyager will continue losing power. The team will continue choosing which functions to preserve. The transmitter and receiver remain essential because a working instrument without a radio link cannot return science. The attitude system remains essential because the radio dish must point toward Earth. Computers remain essential because commands and data need to be organized. Thermal control remains essential because fuel lines, electronics, and sensors operate only across limited conditions. Science therefore competes with the systems that make science reachable. An instrument may be healthy but unaffordable. A heater may appear to produce no data but protect the line that feeds a pointing thruster. A motor consuming 0.5 watts may preserve a future option. The most valuable watt depends on the failure the team is trying to prevent. No responsible source can give an exact final date for Voyager 1. The mission may lose a scientific instrument before it loses communication. It may continue returning engineering telemetry after science ends. A sudden component fault could end a capability earlier than a power forecast. A successful reconfiguration could extend it. This is a genuine unknown with defined causes. It is not the vague claim that anything could happen. Power output can be tracked. Temperatures can be modeled. Thruster performance can be measured. Fault histories can be studied. What cannot be known is which interacting limit will arrive first and whether another workaround will exist. The uncertainty changes how the last years should be understood. Every downlink is not necessarily the final message. Repeating that phrase would create suspense by inventing a countdown. The real tension is quieter and more exact. Each measurement comes from a system with fewer alternatives than it had the year before. Voyager's condition is a record of successful subtraction. Cameras, spectrometers, particle instruments, heaters, and redundant options have been removed from the active configuration. What remains is not the original spacecraft operating unchanged. It is a sequence of redesigned missions inhabiting the same hardware. The team did not plan in 1977 for a one-light-day conversation in 2026. It planned for Jupiter and Saturn, yet the spacecraft's redundancy, command system, reprogrammability, power source, and directional radio made adaptation possible. Later teams used those features in combinations the first mission did not require. This does not mean old technology is magically more reliable than new technology. Voyager has suffered failed components, corrupted data, clogged thrusters, and shrinking power. Its longevity comes from conservative engineering, multiple paths, continuous care, and a trajectory that avoids the atmospheric drag and frequent thermal cycles experienced near a planet. It also comes from accepting a narrower purpose. A probe returning 2 measurements at 160 bits per second can survive on a power level that could not support a planetary imaging campaign. The mission remains valuable because its location makes those 2 measurements unique. By the one-light-day milestone, the live spacecraft will be both less capable and more remote than at any earlier point. The apparent contradiction is the mission's present condition. Less hardware remains active, but every active reading comes from a place reached by no other human-made object. Now compare the power horizon with the distance horizon. The next instrument decision may arrive within years. The inner Oort Cloud may still be centuries away. Passing beyond the cloud may require tens of thousands of years. The electronics and the gravitational journey live on radically different clocks. This is where the phrase "left the solar system" becomes difficult. One definition treats the solar system as the planetary system. It includes the Sun, 8 planets, their moons, dwarf planets, asteroids, comets, dust, and the smaller populations arranged around them. Voyager passed the orbit of the outer planets decades ago. It is far beyond the Kuiper Belt region, occupied by Pluto and many icy bodies. A second definition follows the Sun's plasma and magnetic wind. Under that definition, the heliopause is the relevant edge. Voyager 1 crossed it in 2012, and Voyager 2 followed in 2018. Both now measure interstellar plasma outside the heliosphere. A third definition follows gravitational membership. Which objects remain bound to the Sun even at enormous distances? This domain includes the Oort Cloud, an inferred population of icy bodies extending far beyond the heliopause. These definitions overlap, but they are not interchangeable. A spacecraft can pass the planets while remaining in the solar wind. It can pass the solar wind boundary while still traveling among distant bodies governed by the Sun. It can be on an escape trajectory, while its current location remains inside those populations. The Oort Cloud is not a photographed shell waiting in the darkness. No telescope has returned a family portrait of its members. Its existence and structure are inferred mainly from the orbits of long-period comets that fall toward the inner solar system from many directions. When astronomers trace those comet paths backward and model how planets, passing stars, and the Milky Way's tidal gravity perturb them, a distant reservoir explains important features of the population. The idea is strongly supported, but its exact mass, inner structure, and outer boundary remain uncertain. Cloud can also mislead. It suggests a fog or a continuous layer. The proposed Oort Cloud is an immense volume containing widely separated objects. A spacecraft could pass through its region without approaching any comet closely enough to see. The inner portion may be flattened or torus-like, while the farther population is often modeled as more nearly spherical. Gravitational encounters over billions of years can send some bodies inward and strip others away. The outer edge is not a permanent wall. It is a transition where the sun's hold competes with passing stars and the galaxy. NASA's Voyager FAQ gives a useful scale with honest qualifiers. It may take Voyager 1 about 300 years to reach the inner edge of the Oort Cloud, and possibly about 30,000 years to fly beyond it. About and possibly carry real scientific work. The spacecraft's trajectory can be projected precisely over shorter intervals. The cloud's boundaries cannot. A different definition of the inner reservoir or outer gravitational limit changes the crossing time. Passing stars over thousands of years also alter the dynamical environment. The estimate still transforms the scale. Voyager has traveled for almost 49 years by the 1 light day milestone. That lifetime feels extraordinary because it exceeds the original 5-year mission many times over. Reaching the Oort Cloud's inner region may take several times the entire history of the mission again. Leaving the broader cloud may take longer than recorded human civilization has existed. The 1 light day distance is roughly 173 astronomical units. That is far beyond Neptune's average distance of about 30 astronomical units. It is still small beside an Oort cloud that may extend to tens of thousands of astronomical units. This comparison does not reduce Voyager's achievement. It changes the object of wonder. The probe is not impressive because it is nearly at the end of the solar system. It is impressive because a machine has remained scientifically connected to Earth after traveling a distance that light needs a day to cross, while the larger gravitational system still extends vastly farther. The phrase interstellar space remains correct. Interstellar describes the surrounding medium outside the heliopause. The phrase still inside the solar system can also be correct when solar system refers to the sun's gravitationally bound outer population. Language fails only when it hides the definition. Saying Voyager left the solar system in 2012 without naming the heliosphere encourages the listener to imagine that every solar boundary lies behind it. Saying Voyager has not left the solar system without acknowledging interstellar plasma erases a measured historic crossing. The accurate account needs both. Voyager has left the Sun's realm of plasma dominance along its path. It has not passed beyond the farthest population expected to remain part of the Sun's gravitational family. There is no contradiction once the force is named. Gravity presents another subtlety. It never simply turns off at an exact radius. The Sun's pull weakens with distance, but it extends indefinitely in principle. Other stars and the galaxy also exert gravity. A practical gravitational boundary concerns which influence dominates the long-term motion of an object, not where solar gravity becomes exactly zero. The Oort Cloud's outer region is therefore a dynamical border. An object near it may be weakly bound, perturbed into a new orbit, or removed by another star's passage. The location depends on direction and the changing galactic environment. Voyager is already unbound on its hyperbolic trajectory. If no unexpected encounter changes its path, it will not return to orbit the Sun. That describes its future energy, not its present region. A traveler can hold a valid departure ticket while still crossing the country of origin. The analogy has a limit. Space has no customs post, and the Oort Cloud has no surveyed frontier. The useful relationship is only between trajectory and location. Voyager's path is an escape path. Its current location is still far inside the Sun's broad comet domain, as conventionally described. Even the exact Earth to Voyager distance changes slightly through the year. Earth moves around the Sun faster than Voyager recedes from Earth. During part of the orbit, Earth moves toward Voyager's direction enough for the measured separation to decrease temporarily. The spacecraft never turns around. The distance counter can still move backward. That detail makes the 18 November projection more concrete. 1 light day from Earth is calculated from the moving positions of both objects. It is not simply the moment Voyager crosses a fixed sphere centered permanently on the Sun. NASA's exact time uses mission navigation and the geometry of Earth and spacecraft. The light day threshold will pass without an onboard event. Earth may move in a way that changes the separation around the threshold. What remains is the communication consequence. As Voyager continues outward, the one-way delay stays near and then beyond a day, with small geometric variations on top of the long trend. If the spacecraft were perfectly healthy, this increasing delay would not shut it down. Physics does not impose a maximum communication distance at 1 light day. The signal simply grows weaker with distance, and the response takes longer. The practical end comes from power, pointing, transmitter health, receiver capability, ground resources, and the ability to recover the data. That is why 1 light day is both arbitrary and profound. Arbitrary, because nature does not mark a special surface after exactly 24 human hours. Profound, because a familiar unit of time makes the causal separation impossible to ignore. A message leaves on one date and arrives on the next. An answer leaves the spacecraft and reaches Earth another date later. The machine becomes a correspondent whose every sentence is already history when read. The same was always true at shorter distances. Radio commands to Mars take minutes. Commands to Jupiter take tens of minutes. Voyager's delay grew gradually. Crossing 24 hours does not create latency. It makes latency large enough to span a full cycle of human work and rest. For the spacecraft, nothing about the calendar matters. Its computers count time, execute sequences, and respond to conditions. The day belongs to Earth. One light day is a human measurement placed on the speed limit of information. That human frame is not a weakness. Units exist to connect physical quantities to usable thought. The raw distance of 25,902,068,356 kilometers is precise but hard to feel. A day gives the number consequence. A 2-day minimum conversation turns distance into an operational fact. The Oort Cloud estimate performs the same translation at a larger scale. 30,000 years is not a promise of an exact crossing. It tells us that the object's physical voyage will outlast every powered system, every present institution, and perhaps every recognizable trace of the culture that launched it. Between those two scales lies the life of the mission. Days for a command, years for a power decision, centuries to the inner Oort cloud, millennia to the farther boundary. The next question is not where Voyager ends. It is which Voyager ends first. There is Voyager, the scientific observatory, now reduced to a magnetometer and plasma wave instrument. There is Voyager, the communicating spacecraft, which includes the dish, transmitter, receiver, computers, thrusters, power system, and ground network. There is Voyager, the physical artifact, which can continue after power and contact are gone. And there is Voyager, the body of data already returned to Earth. These 4 versions do not share one ending. The observatory could end one instrument at a time. If power or hardware forces the magnetometer off, the plasma wave system might continue alone. If the plasma wave system ends first, magnetic measurements might remain. The scientific mission becomes narrower with each loss, but it does not necessarily stop in one instant. The communicating spacecraft could survive after the last science measurement. Engineering telemetry might still report voltages and temperatures. A carrier signal might reveal that the transmitter works, even if readable data do not. The 2023 fault demonstrated these layers. Earth still detected Voyager's radio signal, while the information inside it was unusable. The physical artifact needs none of those functions. Once electricity falls below the level required to operate, its trajectory continues. The generators will still contain decaying material and release heat, but not enough usable electrical power for the mission. The dish may lose its aim, thrusters may freeze, or exhaust their practical options. Computers and transmitters may become silent. None of that supplies a force large enough to stop the spacecraft. The returned data have a different durability. They can be copied, reprocessed, compared with new models, and studied after the instrument that made them is gone. A boundary crossing recorded once can answer questions that researchers had not yet formulated at the time. This is already happening. The 2012 heliopause data gained meaning through later plasma wave events. Persistent emission was found by examining a long record, not by waiting for one spectacular moment. Comparisons with Voyager 2 and global heliosphere observations revise the interpretation of a path Voyager 1 has already traveled. A measurement can therefore outlive its original explanation. Directly recorded values remain available while models improve. That is one reason careful certainty matters. If observation and inference are blended into one dramatic claim, future correction can appear to erase the whole result. If the layers are preserved, a model can change while the measurement remains. Voyager's magnetic field surprise provides the example. The field direction did not rotate as the simplest expectation suggested. That did not cancel the particle changes or the density inference. It forced a better account of how the interstellar field may drape around the heliosphere. The mismatch became information. The same discipline applies to the present milestone. The direct projection is a distance and time. The operational inference is a minimum round trip of about 48 hours. The false conclusion would be a new physical boundary or discovery at that distance. One light day does not prove that Voyager has reached a new region. It reveals a new scale of separation in the human part of the experiment. Consider a command to adjust a heater after the milestone. Before transmission, engineers simulate the sequence on Earth. They check which loads are active, how much power margin is expected, what fault protection could do, how the change affects temperature, and whether the antenna schedule allows a confirming downlink. They are planning for a spacecraft they know only through yesterday's report. The command leaves Earth. During the next 24 hours, no update can overtake it. A later warning sent from Voyager may already be traveling inward, but the two signals pass without interacting. Each carries a different slice of history. When the command arrives, the onboard computer validates and executes the sequence according to its rules. If the heater turns on, electrical demand changes immediately at Voyager. Earth remains ignorant. The spacecraft may complete the operation and send telemetry. That answer then needs another day to return. By the time the team sees success or failure, the physical event is about a day old. If the answer demands another intervention, the cycle begins again. This is control without contemporaneous knowledge. It works because engineers predict, constrain, and automate the local response. The method is not unique to Voyager, but Voyager pushes it to an extreme no operating spacecraft has reached before. The delay also shapes science. A plasma wave event happens at Voyager. The measurement is stored or transmitted. Scientists receive it a day later. That latency rarely harms the science, because the event itself cannot be revisited with a quick response. Voyager follows one path and observes what arrives. The greater limitation is bandwidth and instrument availability. For engineering, time can be dangerous because a fault evolves. For heliophysics, the same delay is mainly a timestamp correction. The data reveal what happened at a known place and time, even if Earth learns later. This difference explains why Voyager can remain scientifically valuable when it is operationally slow. The mission does not chase transient targets by turning a camera after an alert. It samples a medium along its path. A magnetic fluctuation recorded today remains a valid fluctuation when received tomorrow. The spacecraft's clock and navigation record connect the measurement to its location. Deep Space Network tracking uses radio timing and Doppler shifts to refine the trajectory. A change in received frequency reveals relative motion. The same radio link carries both scientific content and information about where the transmitter is moving. At one light day, precision is not the absence of uncertainty. NASA can project the threshold to a precise time using an orbit solution, while the actual separation remains sensitive to updated navigation and the motions of Earth and spacecraft. Precision describes the calculation and available data. It does not transform the threshold into a solid object. The distinction between a coordinate and a thing is one of Voyager's recurring lessons. The 100 astronomical unit mark was a coordinate. Becoming most distant was a comparison. One light day is a light time coordinate. The termination shock and heliopause were physical transitions that changed the measured medium. Not every line on a mission timeline has the same reality. The planetary flybys were encounters with massive worlds. The pale blue dot was an observation chosen by the team. The camera shutdown was an engineering action. The termination shock and heliopause were measured environmental changes. The one light day moment is a calculated relationship. The Oort Cloud crossing is a distant model-dependent estimate. The end of contact is a genuine unknown. Placing those events in one list can make them look equivalent. They are not. Their certainty comes from different sources. Direct telemetry documents an instrument turning off. Particle and wave measurements support a boundary inference. Celestial mechanics projects a distance. Comet dynamics supports an outer reservoir. Future component behavior remains uncertain. The mission becomes more interesting when those differences are visible. Voyager is not one endless series of records. It is a chain of changing evidence. Its planetary phase taught through images and close encounters. Its heliosheath phase taught through particle flows and fields. Its boundary crossing required a collision among measurements and models. Its interstellar phase traces a medium with instruments never designed around the questions now being asked. Its final engineering phase turns watts, memory locations, and thruster heaters into scientific decisions. The one light day milestone joins every phase because it measures the consequence of the path. Jupiter and Saturn supplied the trajectory. Titan committed Voyager 1 to a route above the planetary plane. Decades of flight expanded the radio delay. Instruments proved that the path crossed the heliopause. Engineering keeps the connection alive as the light time approaches a day. No single phase explains the distance alone. The gravity assist deserves one more return here. Voyager's speed did not come from an enormous engine that has burned for 49 years. Most of the journey has been a coast. The giant planets redirected and changed its heliocentric motion during brief encounters. The spacecraft now continues because motion does not require continuous thrust in empty space. Thrusters are used mainly for orientation and small corrections, not to drive Voyager outward like a rocket in constant flight. If they stop, the spacecraft does not halt. It loses the ability to point and communicate accurately. This separates motion from mission once again. The outward voyage is easy to continue mechanically. The scientific relationship is hard to continue electrically and geometrically. The Sun also continues without needing to catch Voyager. Gravity weakens with distance, but keeps altering the trajectory. Light and solar disturbances travel outward. The heliosphere moves through interstellar material. The Oort Cloud's comets respond to the combined pulls of sun, stars, and galaxy. Voyager is interstellar without being isolated from its origin. That sentence can now be explained in physical terms. Interstellar refers to the plasma around the spacecraft. Not isolated refers to gravity, light, solar-driven disturbances, and radio communication. Origin refers not only to Earth, but to the planetary encounters that created the path. The spacecraft's two remaining instruments sit on opposite sides of that idea. The magnetometer measures a field shaped by the interstellar environment and the nearby heliosphere. The plasma wave subsystem measures local electron behavior, sometimes excited by disturbances that began at the sun. The instruments are outside the solar wind bubble, while still recording its interaction with the galaxy. This is the beyond-click gain of the distance story. The one light-day number first appears to be about remoteness. The evidence turns it into a story about connected systems. Planetary gravity, solar plasma, interstellar matter, radioactive power, radio waves, ground antennas, old code, and human decisions all meet at one moving machine. The machine is remote because the connection takes time. It is scientifically valuable because the connection still exists. What could the final active years add? The plasma wave instrument may continue tracing electron density as Voyager moves through the very local interstellar medium. Changes in the persistent emission can test whether the inferred density trend continues. Stronger shock-driven events can reveal how solar disturbances propagate beyond the heliopause. The unresolved cause of the weak emission can be compared with new data. The magnetometer may continue recording field strength and direction. Those measurements can test how far the heliosphere's draped magnetic environment extends along Voyager's path and how local fluctuations behave. Neither instrument can map the whole heliosphere alone. Voyager follows one line. A changing measurement can reflect structure in the medium, time variation in the source, or both. Global observations and models remain necessary. The scientific value lies in combining methods, not asking one aging probe to settle every question. Some questions may remain unanswered when contact ends. Researchers may not know exactly where the heliosphere becomes undisturbed interstellar medium, because the sun's influence has several forms and local conditions vary. The persistent plasma wave mechanism may remain contested. The global heliosphere shape may continue to change as models improve. An ending that preserves unknowns is not incomplete. It identifies which measurement would be needed next. A future interstellar probe with modern plasma, particle, field, dust, and imaging instruments could follow another direction, make direct density measurements, and observe the boundary with a design built from Voyager's lessons. Such a mission would still face light time. Better electronics can process more data and manage more autonomy. More powerful transmitters and improved ground arrays can extend communication. None can outrun the wave. Voyager's approaching delay is therefore not a relic of 1970s technology. A modern probe at the same distance would share the 24-hour one-way minimum. Technology changes the quality and quantity of the exchange. Relativity sets its earliest arrival. This makes Voyager a demonstration of a rule that will govern every future interstellar mission. The farther an explorer travels, the more intelligence and resilience must exist at the spacecraft. Earth can provide goals, software, and carefully tested interventions. It cannot provide immediate supervision. At a nearby star, the delay would be measured in years rather than days. A spacecraft would have to handle faults, choose observations, and adapt long before a command from Earth could respond. Voyager is not close to another star, but its one-day delay is the first human-made step into that operational regime. The comparison has to remain proportional. One light day is tiny beside the more than 4 light-years to the nearest star beyond the Sun. Voyager is not about to arrive at a stellar system. At its present speed, stellar encounters occupy timescales far beyond the mission. The valuable lesson is not that Voyager has nearly crossed interstellar distance. It is that even the first day of light time changes the character of control. The Oort Cloud scale reinforces this. The Sun's family of distant comets may extend through a small fraction of the distance to neighboring stars. The boundary between stellar domains is shaped by gravity over immense time. Voyager's radio lifetime occupies only the opening portion of that geography. When communication ends, the spacecraft will continue carrying a directional dish aimed according to its last successful control, though small motions will eventually alter that orientation. The long booms and record will remain attached unless impacts or material degradation change them. The path will continue through a medium so thin that drag is negligible for the foreseeable voyage. Predicting the artifact's exact condition thousands or millions of years ahead would be speculation. Dust impacts, radiation, thermal cycling, and material aging accumulate. Passing stars and galactic gravity alter trajectories. The defensible statement is simpler. Loss of power does not stop inertial motion. The golden record then becomes physically present but functionally unread. Its instructions assume a finder capable of intercepting the craft and interpreting the symbols. No evidence says that will happen. The record's purpose is symbolic and conditional. Its presence still sharpens the ending. The live mission sends changing measurements toward Earth. The record carries a fixed selection of Earth outward. One channel updates every time Voyager transmits. The other was closed before launch. The radio tells Earth about the environment Voyager enters. The record tells a hypothetical finder about the environment Voyager left. When the radio stops, only the fixed message remains aboard. The scientific conversation ends, while the artifact continues as an unobserved object. This gives the title Promise its final answer. Voyager 1 is approaching 1 light day from Earth. The milestone means a radio signal needs 24 hours to cross the distance. A command and immediate reply need about 48 hours before operational delays are added. It is a first for a human-made object, and it changes the tempo of every repair and every confirmation. Voyager 1 entered interstellar space on 25 August 2012. Particle populations changed, and plasma wave frequencies revealed a much denser medium beyond the heliopause. The conclusion came from measurements and inference, not from a photograph of an edge. Voyager 1 has not left the solar system under the broader gravitational definition. The Oort cloud is inferred from comet dynamics and extends far beyond the heliosphere. NASA estimates about 300 years to its inner edge, and possibly about 30,000 years to pass beyond it. All three statements survive because each names a different physical relationship. The heliopause asks which plasma dominates. The Oort cloud asks which distant objects remain bound to the sun. One light day asks how long information needs to travel from Earth. The first answer is interstellar. The second is still within the sun's distant family. The third is one day each way. The larger consequence appears only after combining them. Voyager's mission will probably end while the spacecraft is still deep inside the sun's broader gravitational domain. The radio will fall silent long before the voyage reaches the region where the farthest solar comets move. The event people may call the end of Voyager will not be the end of Voyager's motion. This is the distinction the distance headline cannot carry by itself. The mission is not the machine. The machine is not the data. The data are not the model. Each can continue after another ends. The engineers preserve the mission by changing the machine. The scientists preserve the observations by changing the model. The trajectory preserves the voyage without either one. The honest boundary remains. No one knows the final day of contact. No one can promise the result of the planned Voyager 1 power swap before it occurs. No one can draw the Oort cloud's exact outer surface or predict the artifact's remote future as if it were observed. What is known is already enough. A spacecraft built for a 5-year planetary mission has operated for almost half a century. Gravity from worlds it visited once placed it on an escape path. Instruments designed before launch recognized a plasma boundary that no previous machine had crossed. A failed memory chip was bypassed by splitting code across the remaining space. Thrusters dormant for 21 years were restored to protect the pointing needed for contact. 2 instruments still measure magnetic fields and plasma waves outside the heliopause. And soon, every one of those measurements will arrive from at least 1 light day away. The signal will be weak. Its data rate will be small. Its news will be a day old. Yet the fact that it arrives will close a physical chain from interstellar plasma through an instrument and a 1970s computer, across a radio link, into a dish on Earth, and finally into an explanation of where the sun meets the galaxy. That chain is Voyager 1's most extraordinary remaining instrument. It is made from hardware, physics, and people, separated by a full day of light. When the chain finally breaks, the boundary will not appear on any map. There will be a last measurement received, a last carrier detected, or a last command that never produces a readable answer. The exact form may not be obvious at first. Teams may continue listening and testing because silence can have several causes. Only later will a final exchange become final history. The spacecraft will not know that the relationship has ended. It will continue along the path set by Jupiter, Saturn, and Titan. The heliopause will remain behind it. The Oort Cloud will remain ahead. The golden record will remain attached. Earth will continue moving around the Sun, and the distance will continue to grow. Voyager will then be interstellar in its surroundings, solar in the gravity that still defines the region, and human in the origin of the object. One light day is not where it leaves us. It is where the time between us becomes impossible to overlook.